Stokes theorem states that the surface integral of a curve of a function over a surface bounded by a closed surface is equal to the line integral of a particular vector function around that surface. Okay, so you have to know that the cross product of the gradient and the vector field will give you the curve, right? And n is the normal. So in this video, I'm going to verify Stokes theorem using a question. So for the vector field, which is in terms of x, y, and z, is equals to x plus y squared I, y plus z squared j, z plus x squared k, and c is the triangle with the vertices. So are given 1, 0, 0, 0, 1, 0, 0, 0, 1, and we have to verify Stokes theorem, right? Okay, so first of all, what we're going to do, we're going to sketch a triangle in space, right? Okay, so these are coordinates. We have z, we have y, and we have x, right? So let's sketch the point. So I'm going to assume that 0, 1, 0 is right there, then 1, 0, 0 right there, and 0, 0, 1 right there. Okay, so 1, 0, 0. So that means we're going to move by 1 point from the origin along the x-axis, right? And for z and y, it's going to be 0. Then 0, 1, 0. That means we're going to move 1 point from the origin to the y-axis, and we're not going to move any point from the x or z axis. Okay, then 0, 0, 1. That means we're going to move upwards from the origin by 1, right? Okay, so I'm going to put the coordinates. So this is 1, 0, 0. This is 0, 1, 0. And this is 0, 0, 1. Okay, so now it's time to draw the plane, right, which is going to cover this one. So if we draw, we're going to see this is the triangle that we have, right? So it's a tetrahedron. Our surface is oriented counterclockwise, so this is the arrow, right? This direction that we're going, and we're going to put the normal, right? So the normal, just a plane which is perpendicular to the surface. Okay, so with this, and I'm going to label, as you can see, we have 3 lines here. I'm going to label this one C1, C2, and C3, right? Okay, so now I'm going to use Stokes theorem, right? Instead of taking the individual line integrals, right, for this surface C1 plus C2 plus C3, just going to use a formula and find the line integral. Okay, so let's do that. But we have a problem right here. We don't have the equation of the plane, right? So we have to find the equation of the plane. So I'm going to list, let's say my point A is 1, 0, 0, point B is 0, 1, 0, and point C is 0, 0, 1. Okay, so there are many methods to find the equation of the plane, but I'm going to use this one. I'm going to use the determinant formula, right? Okay, so on the determinant formula, I'm going to assume that A is x1, y1, z1, then B is x2, y2, z2, then C is x3, y3, z3. Okay, so this I'm just going to draw my determinant, right? Okay, so by using the determinant formula, this is what we're going to have, right? So the first right here, we're going to have x minus x1, right? And we have x1, x2 minus x1, x3 minus x1, same as here, y minus y1, y2 minus y1, y3 minus y1, z1 minus z1, z2 minus z1, and z3 minus z1, and this should be equal to 0, right? So that we can find the equation. So now it's a matter of substituting, right? So I'm going to have x minus 1, right? And remember, x2 is 0, x3 is 0, right? So it's just a matter of substituting, right? So now let's simplify, right? So just going to have x1, and 0 minus 1 is negative 1, right? And 1 minus 0 is 1, right? So now to find the determinant, right, what we do, we first of all, we take x minus 1, right? Okay, and after that we're going to close this column and this row, right? And we're going to take this matrix, right? Okay, so let's do that. Okay, I'm going to write it new here. So I'm going to have x minus 1 and close. Okay, so this is what we're going to have, right? And for y, remember, for y we put negative, right? And if we put negative, we're going to close right here, close this row, and we're going to close this column, right? So as you can see, we have negative 1, which is right here, and we have 1, which is right here. We have negative 1, which is right here, and we have 0, right? And for z, we're going to have, it's going to be positive, right? So it's plus, negative, and plus, right? Okay, so that's the sequence. So for z, what we're going to do, we're going to close this row, this column, and this row, right? And we're going to have negative 1, which is right here, negative 1, 1, 0 right here, as you can see, 1, 0 right here. Okay, so now let's take so now it's time to find the determinant of 2 by 2 matrix. So I'm going to say the blue diagonal, right, as you can see, and we're going to subtract it by the red diagonal. Okay, So that's what we're going to do. And what we're going to have, if we say 1 times 1, we're going to have 1, and 0 minus 0 is just going to have 0. That's why I've not written 0, right? And here we're going to have negative y. Remember, if you say negative 1 and positive 1, we're going to have negative 1, right? And the 1 times 0 is going to be 0, so that's why I haven't write it, right? And right here for 0, right? If you say 1 times 0, we're going to have 0, right? But remember, we're going to put a negative, right? Since we said we're going to say blue diagonal minus red diagonal, right? And we're going to have negative 1 times 1, so that's why I put a negative right here. Okay, so now it's a matter of simplifying. So we're going to have x minus 1 plus y plus z equals to 0. So we're going to move on to the other side. So this one is the equation of the plane. Okay, so now with the equation of the plane, what do we need to do? So it's time to find the KO, right? We're going to find the cross product of the gradient and the vector field. Okay, so let's do that. Okay, so this is the formula, right? So we're going to have I, j, and k. Here we're going to have partial x, partial y, partial z. And I, right, here is the I component, as you can see, x squared plus y squared, right? And j is the j component, and k is the k component, right? So that's what we have to do. That's what we have done, right? And now repeating the determinant formula, right? Like what we did. What we're going to do, we're going to start with I, right? So from here, this is what we have. Okay, so now first of all, we're going to close I, right? Okay, so for I, right, we're going to put I, positive I, negative j, and positive k, right? You know what we have done, right? And now what we're going to do for I, we're going to close this row and this column, right? And after that, we're going to say partial y times z x squared, right? As you can see right here, and we're going to subtract that by partial z of y plus z squared, right? So that's what we have done. And for j, right, we have put a negative right here. Okay, always put a negative, and we're going to close this row, this column, and this row, right? Okay, so now we're going to say partial x z plus x squared, right, minus partial z x plus y squared, right? So that's what we've written here. And for k, it's going to be positive, right? And we're going to close this column and this row, right? So we're going to say partial x y plus z squared minus partial y x plus y squared, right? Okay, so now it's a matter of partial differentiation. So here it's partial y. That means we're going to differentiate everything with respect to y, but don't have y here, so it's going to be 0 right here. What about here? We have y plus z squared. So if we differentiate y with respect to z, it's going to be 0 because it's a constant. But for z squared, it's going to be 2z, right? Okay, so right here for partial x of z, it's going to be 0, right? But for x, right, it's going to be plus 2x, right? Since we're going to differentiate with respect to x, right? And right here for partial z of x, it's going to be 0. Of y, it's going to be 0 again, right? Okay. And right here partial x of y, it's going to be 0. Partial x of z is going to be 0, right? Because we're differentiating respecting to x, so that means everything will be equal to everything will be constant. That is x and that is y and z, right? And right here, partial y of x is going to be 0, but partial y of y squared is going to be 2y, right? Okay, so now let's see what we're going to have. So this is what we're going to have. We're going to have 0 right here, and we have negative 2z, right? And right here we're going to have 2x, right, minus 0, and here we're going to have 0 right here minus 2y. So now it's a matter of simplifying, right? Taking note of the direct number. So we're going to have negative 2zi, negative 2xj, and negative 2yk, right? Okay, so this one is our KO. Okay, so now I'm going to write my KO right here in the equation of the plane, right? So now what we need to find NTS. So the main method to find NTS, some people just find the gradient, right, and just multiply that by ds, and the formula for ds is x squared plus y squared plus 1 or under the square root. Okay, so but what I'm just going to use right here, I'm going to use a simple Jacobian, right, and find the cross product of a Jacobian, and that will give me NTS. Okay, so what I'm going to do, I'm going to make this of the formula first, right? So this is just putting y and x on the other side, right? Okay, so this is what I have, right? And now I'm going to write my new vector, right? So I want my x to be u and I want my y to be v, right? So that means we've got 1 minus x and x is u, 1 minus y and y is v, right? So this is what I have, right? So that means my vector is going to be r equals to x plus y plus z. Okay, so now I know that NDS is just going to be the Jacobian, right? Since we're going to transform, right, everything that we have, right? So NDS is going to be the cross product of RU times RV du dv, right? Like what we do in Jacobians, right? Okay, so now for RU, that means I'm going to differentiate this vector with respect to u, right? Okay, so as you can see, if I differentiate u, I'm going to get 1, right? So that's why I have I right here. And if I differentiate v, it's going to be 0. So that's why we don't have the j component. But right here, we're going to have -1. So that's why we have negative k, right? And now I'm going to RV. So for u, it's going to be 0. We're not going to have I component. But for v, we're going to have, for j, we're going to have 1, right? Because if we differentiate v, we're going to get 1, right? And right here, we're going to have -1. So it's going to be j negative k, right? Okay, so now let's write the cross product, right? Okay, so I, j, and k. So now it's just a matter of finding the determinant, right? So first of all, remember it's going to be plus, minus, and plus right here. Okay, so now let's do that. Okay, so for I, we're going to close this column and this row. And we're going to have 0, 1. As you can see, we have 0, 1 right here. And we're going to have -1, -1, and -1 right here. And for j, this column and this row, we're going to have 1, 0, 1, 0, -1, -1, -1. Okay, and now for plus k, closing this column and this row. Okay, now we're going to have this, right? As you can see, this is the matrix that we have right here. So now it's just a matter of finding the determinant. So now to find the determinant, what we're going to do, just going to say this diagonal, right, minus this one, right? And right here, this diagonal minus this one, this diagonal minus this one, okay? Like what we did before. And if you do that right here, I'm going to have 0 times the -1 is going to be 0, and we're going to put a negative, right? Then 1 times -1, and we're going to have -1. So that's why I have a negative and a negative right here. And right here, we're going to have 1 times -1, right, minus 0. So that's just return -1. And right here, we're going to have k, and we're going to have 1 times 1, right? Okay, so now let's simplify. So we're going to have I plus j plus k, right? Okay, so now we have everything, but what we don't have are the limits, right? We don't have limits. So what are we going to do? Okay, so let's look at our plane, right? So this is our plane, right? So what we need to do, we're just going to project this in the xy plane. Okay, so if we do that, this is what we're going to have, right? As you can see, so this is the xy plane. So this is the chart where we get limits, right? Okay, so I'm going to sketch xy plane right here. This is what we have. So now by using y minus y is 0 is equal to m x minus x is 0, right? Okay, and you have to know that m is the gradient. So the gradient of this one is going to be 1 divided by 1, right? But still it's decreasing, right? You can see it's decreasing. So it's going to be -1, right? So m is going to be -1, okay? So now it's a matter of substituting, right? Okay, so by choosing this point, so at this point you should know that the coordinate of y is 0, right? So I'm going to say y minus 0, -1, x minus 1. And if I simplify, I'm going to have y equals to -x plus 1. And I'm going to write the equation of this line, right? So now it's a matter of limits. So x ranges from 0 to 1, okay? So let's write the limits for x. But what about y? So as you can see, y ranges from 0, and right is going to touch this line. 0 is going to touch this line. 0, touch this line, 0, touch this line. Okay, so you can just say that the limits for y is going to be from 0 to the equation of that line, right? Okay, so now let's write what we have right here. We have our limits and we have our change variables. Okay, our limits, so for u, which is equal to x, right, and y is equal to v, right? So right here, as you can see, it's -x plus 1. So that's why I said -u plus 1. Okay, so this is what we're going to have, right? double integral. So I've just written this in this form, right, in column form, right. That's the form that I prefer. So this one is the curl, and this one is the cross product of RU and RV. Okay, so just since it's the dot product, it's going to be is, right, we're going to say negative 2z times 1, negative 2x times 1, negative 2y times 1, right? And if we do that, this is what we're going to have, right? Okay, negative 2z, negative 2x, negative 2y. So you can just factor out negative 2 right here. As you can see, you're going to be left with z plus x plus y. But we have z, right? We know that z is equal to 1 minus u minus v. You know that x equals to u and y is equals to v, right? Okay, so by substituting those values, you can see it's what we're going to have, right? Okay, so right now let's just move the brackets. Okay, so this is what we're going to have, right? So now it's going to be v minus v, u minus v, and we're going to be left with 1, right? Okay, so let's integrate 1 with respect to v. It's going to be simple, just going to be v, right? And we're going to put the limits from 0 to negative u plus 1 du. Okay, so by saying upper bound minus lower bound, we're going to say negative u plus 1 minus 0. Okay, and what we're going to have, we're going to have negative u plus 1 du. Now let's integrate with respect to u. So for negative u, it's going to be negative u squared over 2. Then for 1, it's going to be plus u, right? So that's what we're going to have. Upper bound minus lower bound. So it's going to be negative 1/2 plus 1, and that's going to give us positive 1/2 times negative 2, and we're going to have negative 1, right? So this is line integral, right, of the surface of the tetrahedron. So now I want to verify it using the other side. Okay, so I'm going to start with C1, right? So if you're not good at line integrals, I hope you watch this video, right? I've solved many complex path, right? Any path that you need, right? So after watching this video, you'll be able to solve any line integral problem, right? Okay, so FDR is going to be the sum of C1 plus C2 plus C3, right? So now let's start with C1. So for C1, you can see this is the line, right? And right here we're at the base, right? And we have to agree that C equals to 0, right? In the equation of this line, right, we have calculated this equation, right? It was y is equal to negative x plus 1, right? So by making us up to the formula, we're going to get x equals to 1 minus y, right? So some of you may be wondering why I've made x equal to the formula. So if I look at my vector field, right, you can see we have x plus y squared right here, and that means if y is equal to the formula, that means I have to expand a very long brackets, right? So to avoid that, I'm going to make x my dependent value, right, as you can see, so that y will be independent. So for y squared, I'm just going to write y squared, right? And for x, it's going to be 1 minus x, right? Then writing negative x plus 1 squared, it's going to be hard to expand the bracket, right? The values for y, right? Let's go to limit for y. So right here, y was 0, right? You have to agree that. And right here, y is 1, right? Okay, so in line integral, you have to take note of where you are coming from and where you are going, right? And this is the case so you can have the upper bound being lower than the lower bound, right? Okay, so now let's go for x, right? So I'm just going to draw this graph right here. Okay, so for x, you see, if say y ranges from 0 to 1, right, and x is going to range from 0 to this line, 0 to this line, 0 to this line, 0 to this line, going so on, right? So it's going to be 0 to 1 minus y, right? And let's differentiate z with respect to x, right? So we're going to have dz dx be equal to 0. And let's differentiate y with respect to x. So we're going to have dx be equal to negative dy, right? Okay, so now let's write our vector, our integral problem, right? Okay, so it's going to be x plus y squared dx, y plus c squared dy, and z plus x squared dz, right? So remember, r is dx, j dy, and k is dz, right? So now let's substitute, right? Okay, and for x it's going to be 1 minus y, and for y it's y squared, right? You see what I was trying to say, right? So if this was in terms of x, we're going to have 1 minus x squared, and we have to expand that bracket, and that was going to be difficult, right? Okay, so right here for dx, right, you say dx is equal to negative dy, since we're dealing in terms of y, right? Okay, no, our limits are in terms of y, right? Okay, so for dy it's going to be dy, and for dz, that's why I've not substituted anything right here, because I know it's going to be equal to 0, right? Okay, so now let's simplify right here. Okay, so by multiplying each and every term by negative, I'm going to have -1 here, +1, and negative y squared, right? Okay, and we're going to add y, right? So it's going to be -1 plus y plus 1 minus y squared. And if we do that, we're going to have 2y minus 1 minus y squared. Now let's integrate. So this is to integrate. So we're going to have we're going to have positive 2y squared over 2, negative y to the power 3 over 3, right? And you can see if we divide here, just going to get y squared, right? And if we substitute for 1, we're going to have 1 minus 1 minus 1/3, right? And for 0, everything will be equal to 0, so let's just ignore it. And we're going to have negative 1/3. Okay, now let's go to line number 2, which is going to be C2, right? Okay, so as you can see, this is C2 right here. And at C2, we have to agree that you can see that x right here, the value of x, right, is 0, right? Okay, and I'm going to write my equation in terms of z. So why I'm writing my equation in terms of z, you can see right here we have z squared. So if we write it in terms of y, we have to expand the bracket, and we don't need that. We just want to do these things, right? Okay, and for the limits, so for z, you can see that z ranges from 0, z was 0 right here, and it goes up to this point, right? And it's now 1, right? Okay, and for y, so y, let's draw this graph, right? You can see from here to here, I'm going to touch this line, here to here, I'm going to touch this line, here to here, I'm going to touch this line. Okay, just like what we did. So it's going to be from 0 to 1 minus z. So now let's differentiate x with respect to z. It's going to be 0. Okay, and if we differentiate y with respect to z, we're going to get our dy because negative z. So let's substitute right here. We said I is dx, j is dy, and k is dz. Dx is going to be equal to 0, so there's no need for substituting anything right here. Just going to leave it like it is, right? And for y plus z squared, right, and y is going to be 1 minus z and z squared, right? Okay, and for dy it's negative dz, and right here x is 0 dz, right? So now let's simplify, right? Okay, so if we multiply everything by negative, right, we're going to see that we're going to have -1 and negative z -1 is going to be positive, right? Okay, and for positive z squared is going to be negative z squared plus z. So now let's say it like terms. Okay, so we're going to have -1 plus 2z minus z squared. And if we integrate, we're going to have positive z squared over 2 minus z to the power 3 over 3. And we have our limits. So now it's a matter of substituting, right? And if we substitute, we're going to have right here, you can see we have 2 and 2, and that will give us 1, right? So we're going to be left with 1 minus 1 minus 1/3, and that is going to give us -1/3. So now let's go to the final line, and this one is going to be C3, right? Okay, so right here we chose x to be the independent variable. So you can see the value of x was 0, and right here it's going to be 1, right? So these are going to be the limits for x, and for z, I'm going to just sketch the cx plane, right? So it's going to be, you can see from here to here, it's going to be 1 minus x, 1 minus x, 1 minus x. So you're just going to put the equation of that line, right? Okay, so dy is equal to 0, and dz is going to be negative dx, right? Okay, now let's put the limits. So we're going to have x squared plus y squared, and said I dx, j dy, and z and k dz, right? Okay, but since I know that dy is going to be 0, I'm not going to substitute anything right here. Just going to leave it like it is, right? Okay, so I'm going to have x plus y, which is 0 dx, right? And right here it's going to be 0. For z is going to be 1 minus x plus x squared negative dx. It's time to add like terms, right? So I'm going to have x plus 1. If you factor out dx, right, I'm going to have 2x minus 1 minus x squared, right? Okay, and if we integrate, we're going to have 2x squared over 2 minus x to the power 3 over 3, right? And again, divide this, okay? And now what we're going to get, we're going to have -1 minus 1 minus 1/3, right? And that is going to give us -1/3, okay? So this one is not there, right? Just going to add, right, line integral. So we're going to be -1/3 plus -1/3 plus -1/3. And if we do this, we're going to have -3 over 3 and -1, right? So as you can see, we have verified the Stokes theorem. So thank you for watching. If you benefited from this video, don't forget to subscribe.